Today, we will be making this Boids animation using geometry nodes in Blender 4.1. The system will work by having a large simulation zone with a repeat zone nested inside of it to calculate the new Boid trajectories. The Boids algorithm simulates bird flocks. The word Boid actually refers to a bird-like object, and yields surprisingly complex results based on 3 simple rules. We will be implementing a configurable system to simulate all 3 of these rules in geometry nodes: cohesion, alignment, and separation. Start off by creating a new Blender project. Again, I'm running version 4.1.0. Next, press Shift-A to enter the Object Addition menu, add a cube, and then enter the Geometry Nodes editor by pressing the option on the top bar. Create a new Geometry Nodes project by clicking the New button in the middle of the screen. Disconnect the group input geometry from the group output geometry. We are doing this because we are not actually going to use the cube we created earlier. Instead, we are going to pass points through a simulation zone. This node works by repeatedly performing some operation on the input, using its own output as the next frame's input. Press Shift-A and search for Simulation Zone. Then, connect the output of the zone to the Group Output node. Now, add a points node and connect it to the Simulation Zone input. These points will act as the Boids in our simulation. Every frame, each point will pass through the simulation and get changed in some way. Then, this new state will be outputted and passed back into the simulation, continuing the process. We want to spread these points out randomly though, instead of all of them being in the same spot. So, add a random value node, switch it to vector, and connect it to the position socket on the points node. Set the minimum vector to -10, -10, 0, and the maximum to 10, 10, 0. Now, if you increase the number of points, they will be spread out within that boundary, as their position is being manipulated by that random value node. This is up to preference, but I prefer to disable the 3D cursor in Origins, and to enable the cavity option in the modeling window, just so that the points stand out a bit more and there's less clutter on the screen. Now that we have our points, we want to change them to move with some kind of velocity every frame. Doing this with simulation nodes is quite simple. Add a set position node and drag it onto the geometry. Then, click the simulation zone node and press N to open the node editor window. Navigate to the node tab and click the small plus icon on the right to add a new property. Change it to a vector and name it velocity by double-clicking on it. Connect that new property to the simulation output and also connect it to the offset of the set position node. With this setup, our velocity will remain constant and our points will all be offset by the same velocity every frame. If every particle moved in the exact same way, it wouldn't be particularly interesting to look at. So, to remedy that, duplicate the random value node we created earlier and change its seed to a different number. Then, connect it to the initial velocity input of the simulation zone. Now, add a vector math node and set it to normalize. Place it between the 2 nodes. Normalizing a vector transforms it to have a length of 1, while maintaining the same angle. With this node, all the points will move in different directions, but at the same speed. This velocity vector will be important later on. In order to access it later, we need to associate each point with its velocity by utilizing a named attribute. This way, we can access the velocity later by calling on the attribute. Add a store named attribute node and place it on the geometry line. Set it to vector, connect the velocity as the value, and set its name to velocity. Now, let's define what we're trying to do to each velocity. Suppose we have a point, which is our Boid, and it has a certain radius of vision around it. Let's say all the Boids within that radius have a specific velocity and position value assigned to them that we can access. So, what do we want our new velocity to equal? Firstly, we want to compute the average position of all the Boids within that vision radius, and we will add that to our current velocity. Then, we also want to add the average direction of all the Boids in front of us. So we want to take each angle and make a new vector based on that, all the vectors combined. Thirdly, we want to have a second radius, a smaller one, and if there are any Boids within that radius, we want to steer away from them. This will be our separation component. For the average position and average velocity, we will need to know the number of neighbors within our defined vision of each Boid. And once we have all those things computed, we can add them all together to get our new velocity. Now that we know what to do, let's get to implementing this system. Simulation zones work by looping over every point that is inputted at the start, and we will use that point as the reference position. In order to access the attributes of points only within a specified radius of that reference point, we need to iterate over every single other point. In geometry nodes, this is done using a repeat zone. As per the name, the repeat zone will repeat whatever is inside of it by a certain number of iterations. Add a repeat zone and place it somewhere in the middle of the setup. For ease of use, place a group input node, and using the side panel menu, make a new value, an integer, and name it count. Plug this new input value, which we can now change in the modifier stack, into the point count and the iteration socket of the repeat zone. This way, the number of iterations will be the same as the number of Boids in the simulation. In order to find the new velocity, we need to define a sample or reference position that we can draw the radius from. We can draw this position straight from the simulation zone. To extract an attribute from the points, we can use a capture attribute node. To specifically get the position, add a position node and set the capture attribute node to accept vectors. Connect the position as the value. The output of the capture attribute node now is the position of the Boid we are evaluating. Now, take the output position and connect it to an empty socket of the repeat zone. We can now reference this position while iterating. Using the side menu, rename it to sample position. Connect the sample position through the repeat zone so that it stays as a constant every iteration and does not change. Right now, the repeat zone is iterating over nothing. In order to access every Boid's data, we need to tell Blender which one we want to look at. In geometry nodes, each point is represented by some index. You can see this value in the spreadsheet in the top left corner in the leftmost column, and this value starts at 0. If you've programmed something using lists before, this is probably familiar. Since there are as many indexes as there are points, each iteration of the repeat zone should look at a specific index. To sequentially loop over every index, say 0, 1, then 2, then 3, then 4, and so on, we need another variable. Using the side menu and the node tab again, with the repeat zone selected, make a new value of type integer. Connect it through the zone, and this time, instead of letting the value be constant, add a math node set to add a value of 1. This way, each time the cycle repeats, there will be a new, unique index that corresponds to some point. Using the index, we will be able to compare the reference position defined earlier with the position of another point. Now that we're iterating over every point, we can extract attributes from those points for comparison with the reference position. To access the position of a point based on its index, Geometry Nodes has the Sample Index node. Add one and connect the index and geometry to it. By comparing some point's position to the sample position, we can determine if it is within the radius, and from there whether or not to include it in the velocity calculations. So, add a position node and connect it to the value of the sample index node. To find the vector between the sample position and the new position, add a vector math node set to subtract. Connect the sample position to the bottom slot and the sample index node's output to the top slot. This subtracted vector goes from the sample position to the position of the other point. Next, add another vector math node set to length. Since the subtract node outputted the vector from the sample position, the length is the distance between the 2 points. Finally, add a compare node set to less than or equal to check if the point is within the specified radius. For ease of use, add a group input node and add a new value set to distance named threshold and connect it to the compare node. Now, we have a boolean that specifies whether or not a point is within the radius that is defined in the modifier. The first value we will compute will be the number of neighbors. Create a new integer socket in the repeat zone using the side menu, named number of neighbors. Pass it through the zone. Then, add a switch node. This node, as the name suggests, switches a value when a boolean is true. Plug the number of neighbors input to the false side and plug the output of the switch node to the number of neighbors output. Then, add a math node set to add a value of 1. Plug the initial number of neighbors value into the A socket and connect the output of the math node to the true input of the switch node. Then, connect the boolean from the compare node to the switch node. Now, whenever a particle is within a radius of the reference position, the number of neighbors value will increase and be switched from the previous value to the value plus 1. The next thing to implement will be the average position. To get an average, you first need to add up all the values. In this case, these values would be the positions of points within the radius. Just like the number of neighbors, add a new tab in the repeat zone named average position. Create another switch node, but set it to vector this time. Connect the Boolean result from the first compare node to the switch, and then set it up in the same way, with the false input of the switch being the previous value, unchanged, and the true value connected to a vector math addition node. To add the new position, use the output of the sample index node from earlier. For the average direction, or average velocity of the points, the setup, again, is very similar. Add another input in the repeat zone, add a switch node, connect it to the Boolean, and use the previous value as the false, and a vector math addition for the true. You may notice that we still have not extracted the velocity from the points. This is what the named attribute was for earlier. By creating that attribute and having the points capture it earlier, we can now access it with using another sample index node. Add one, set it up in the same way as the other one, with the geometry and index being connected. Set the type of value to vector, and add a named attribute node also set to vector. Connect that attribute to the sample index node, and then type in the name that you set earlier into the name tab. Now, connect the output of that sample index node to the vector addition node. Finally, for the separation component, add another tab in the repeat zone and connect it through. Then, add a switch node. Since the separation relies on a different radius or distance, add a new compare node set to less than or equal. Connect it to the length node we used previously and also to another group input node, this time named separation distance. Set it to be a distance value. Connect the new compare node to the switch. For the false input, pass the unchanged separation value through, and for the true input, add a vector math node set to subtraction. The reason we are subtracting is because we want the Boid to move away from other points that are too close. So, we need to add a negated version of a vector instead. If you recall, we previously already made a vector that went from the reference position to the other point's position. Subtracting this vector will steer the Boid away from that point. We have now calculated all three forces in the Boid's algorithm using iteration. Let's quickly summarize what we just did. As I mentioned previously, simulation zones work by individually looping through every point. For every point, we are looping over every other point using a repeat zone to calculate the new velocity. First, we compare the reference position from the simulation zone to the one we are iterating over in the repeat zone. If those 2 points are close enough, we consider them a neighbor and increment the number of neighbors variable. Additionally, we add that point's position and velocity to the respective variables. If a neighbor is too close to the reference point, then we use vector subtraction to create a force away from the neighbor. Now that we have the raw numbers calculated, we need a system to weigh each value differently, for both ease of use and functionality. However, there's still one issue. During our repeat zone calculations, at some point, the index landed on the same point as the one that was being referenced. This means that in order to have only the neighbor's values counted, we need to subtract away the reference point's attributes. Add a math node set to subtract a value of 1. Connect that to the number of neighbors variable. Then, add 2 vector math nodes set to subtract. For the first one, connect the average position on the top and the sample position on the bottom. For the second vector math node, connect the average velocity to the top. To get the velocity of the current Boid, add another capture attribute node and connect it to another named attribute node, the same way we set it up in the sample position earlier. Then, connect the captured attribute to the bottom slot of the vector math node. Currently, we only have the sums of the positions and velocities of the other points. To get that average, we need to divide by the number of Boids evaluated, which is conveniently the number of neighbors value. Add 2 more vector math nodes set to divide. Plug the outputs of the subtract nodes into the divide nodes, and then put the subtracted number of neighbors value into the bottom slot. To make these new vectors easier to work with, add 2 more vector math nodes set to normalize. For ease of use, we will use sliders in the modifier panel to control the cohesion, alignment, and separation forces. Add a group input node, and in the group tab in the side menu, add 3 new inputs. Name them accordingly, and set their subtype to factor. Set their minimum value to 0 and the maximum to 2. To be able to modify all these aspects of the simulation intuitively, we need to change these input values. This will consist of several math nodes. These numbers aren't specifically special, but they are what I found works best. First off, add 2 subtract nodes. Set the top value to 2 for both, and then connect the cohesion and alignment values from the group input. Next, add 2 more math nodes set to multiplication, and multiply the 2 math outputs by 50. Finally, add 2 more math nodes set to add a value of 0.01. These 2 final nodes are for instances where the weights go to 0, and they serve as a minimum. To apply these to the vectors, add 2 vector math nodes set to divide. Plug the normalized vectors into the top slots and the outputs of the math nodes into the bottom slots. Finally, for the separation, add 1 more math node set to multiply a value of 5. Connect the group input separation value to this. Then, add a vector math multiplication node. Connect a separation component from the repeat zone and the math node. To obtain the final velocity, we now need to add all of these values together to the previous velocity. Add 3 vector math nodes set to add. Add the previous velocity, which should still be connected to the set position node from earlier in the process, and the separation component to the first adder. Then, add the previous adder's output and the alignment using the second node. Finally, add the second adder's output and the cohesion values in the last add node. To finalize this new velocity, add 1 more normalized node and 1 more vector multiplication node to the setup. Set the multiplication node to 2, 2, 0. We can use this multiplier as a way to control the general speed of the simulation. Connect the multiplication node to the set position node that we created earlier. We have now technically finished the Boids algorithm, having implemented all 3 of the rules. However, if you run the simulation, you will notice that the Boids all scatter off in different directions and don't ever stop. To keep the Boids within an enclosed boundary, we need to create another force, a border, that pushes Boids away when they get too close to a boundary. Creating a border will consist of checking the x and y components of the Boid positions, and then adding a force away from the border if the position is over the limit. For example, if a Boid goes too far on the x-axis, a vector of -1, 0, 0 would be added, which would push the point to the opposite direction. Navigate back to the start of the simulation zone, where we extracted the sample position. Add a separate XYZ node, and plug the position of the point in. Now, add 4 compare nodes. Set 2 to greater than, and then set 2 to less than. Plug the X component into 1 greater than and 1 less than node. Do the same for the Y-axis. To allow for customization, add a group input node, and add 2 new properties using the side menu. Name them X-bound and Y-bound. These will control the size of the border. Firstly, connect the X-bound directly to the greater than node that is connected to the X-axis. Then, do the same for the Y-bound and Y-axis. Since the 2 other compare nodes use less than, add 2 math nodes set to multiply by -1. Connect the X and Y bounds to the math nodes. Then, connect the math nodes to the respective less than compare nodes. Now, the boundary is user editable, and we can tell when a Boid crosses any of the boundary lines through the compare nodes. In order to translate these Boolean results to a vector output, we will again make use of switch nodes. Add 4, all set to vector. Connect them horizontally from the compare nodes. Leave the false vectors unchanged, and for the true vectors, use the following. For the greater than x-axis node, use -10, 0, 0. For the less than x-axis node, use 10, 0, 0. For the greater than y-axis node, use 0, -10, 0. For the less than y-axis node, use 0, 10, 0. Essentially, all that's happening here is that when a Boid crosses the boundary, we get a vector that opposes that boundary. Now, create 3 vector math addition nodes and connect all the switch node outputs. For the first adder, add the first 2 switch nodes. For the second adder, add the first one's output in the third switch node, and so on. Finally, to control the strength of the border, add a vector math multiplication node and connect it to the added up output. Then, add 1 more group input node and create a new variable, set to float and factor, named the border strength. Set the minimum value to 0 and the maximum value to 1. Then, connect the border strength to the multiplication node. To add the new border force to the other velocity calculator, add a vector math node set to add. Add the border vector and the other vector. The output is the final velocity of the Boid. To finish off the project, we need to transform these points into actual geometry. Go into the Model tab, add a plane, go into Edit mode, and select 2 points on one of the edges. Press M and then select at center. This will merge these points together. Then, at the opposite edge, add a loop cut using Ctrl R and then click. Move this new point inwards and then scale the entire plane however you like. Make sure the front end of the plane is facing the positive x-axis. Once you're done modeling, press Ctrl A and select all transforms. You can then hide this plane using H. Go back into the Geometry Nodes editor and go to the end of the network before the group output node. Add a Instance on Points node and connect an Object Info node. Select the plane in the Object Info node and adjust the scale using the Instance on Points node. You will notice that while the plane is being instanced on every point, it's facing the same direction every time. We can fix this using a vector math formula. Given a vector, x, y, its angle from the x-axis is the tangent inverse of y divided by x. To implement this in the Geometry Node setup, add a Separate XYZ node. Then, connect the velocity output of the simulation zone to the node. Add a math node and divide the y value by the x value. Then, add another math node set to arctangent, which is the same thing as the inverse tangent. Theoretically, the output of this node is the angle of this vector. However, it is important to remember that the arctangent operation is limited to a range of negative pi to pi radians, or negative 90 to 90 degrees. This means that the setup can only handle angles up to 90 degrees from the x-axis. In order to account for angles beyond that, we need to add pi radians, or 180 degrees, to the angle if its x component is less than 0. As per usual, to implement this in Blender, we need a compare node and a switch node. Set the compare node to less than and plug in the x value. Then, set the switch node to float and plug the raw arctangent value into the false slot. For the true, add a math node and also plug in the arctangent. For the addition, type pi. Then, connect the add node to the true socket of the switch node. Since we are rotating these points on the z-axis, add a combine XYZ node and plug the switch node output into the z tab. Then, connect the new vector to the rotation tab of the Instance on Points node. We are now completely done with the Geometry Node setup. Hopefully, everything was understandable and clear. I tried to explain what exactly was going on where I could. If you would like to have the same material that is on the screen now, here's a quick explanation. First, add a Capture Attribute node on the main geometry line. Set it to integer and connect the number of neighbors value from earlier. Then, connect the output of the Capture Attribute node to the output of the simulation zone. Add a Map Range node outside of the simulation zone and connect the outputted value. Set the from minimum to 1, and for the maximum, add a group input node and connect the Boid count. Multiply this value by 11. Connect this to the group output node and name it density. In the modifier panel, go into the Output Attributes tab and type in density again. Now, enter the shading window, make a new material, and add an emission node and a color ramp. Then, add an attribute node and set it to density, and type in density. Connect the factor to the factor of the color ramp. Set the color ramp to HSV and clockwise, and then set one side to red and the other to blue. Back in the Geometry Nodes editor, add a Realize Instances node and the Set Material node to finalize the effect. Thank you for watching and listening. If you would like an extra challenge, try and expand the setup to 3 dimensions. Simply adjust the spawning criteria and add another border. The rotation aspect is a bit more tricky. Here's a setup I found that also uses vector math.